Hello, thanks everyone. Thanks for joining today. I'm Eric. I'm the CTO at GuardSquare, and I'm the original creator of ProGuard, the open source optimizer and obfuscator that you may all love, or at least love to hate. Today I'll talk about Kotlin. Not necessarily Kotlin the language or any Kotlin frameworks, but I'll look at what Kotlin looks like inside an Android application after it has been compiled. What does the bytecode look like? What does the application look like that you deliver to your end users? This is partly out of curiosity. I always like to know what's inside my application, but also partly because it's important to know about how it has been optimized and obfuscated. So it's important for size, performance, and maybe security as well. So what are the topics that I'll be talking about today? I'll touch upon the Kotlin runtime libraries that go into Kotlin applications, the bytecode that the Kotlin compiler generates, the metadata that the Kotlin compiler generates, and I'll discuss how that interacts with optimization and obfuscation that you might apply. And I'll try to demonstrate that these are actually still very important and useful when you want to deliver a lean application. So I'll talk about size, performance, and security. As the example throughout my presentation, I'll be using the Google I/O scheduling app. The latest version of that application is written entirely in Kotlin. And if you look at the open source repository, it contains about 300 source code files in Kotlin and more than 100 libraries. And all of that amounts to 176 jar files, which get compiled onto 16 Dex files. So the jar files are Java bytecode, the Dex files are Dalvik bytecode, and that gets packaged into an APK that is about 13 megabytes. As you can see in this slide, the numbers, Java bytecode is bigger than Dalvik bytecode. Dalvik bytecode has been designed to be more compact. And maybe somewhat surprising, the Dalvik bytecode is bigger than the APK because the APK is able to compress a lot of the code and assets that go into the application. So this is the starting point, and I'll start by looking at some of the libraries. I'll zoom in on the Kotlin libraries that have gone into that application. If you're using Kotlin, you're no doubt aware that you're using the standard library there, and that is in its Java class file form about 1.4 megabytes. There is an additional common library that is 180 kilobytes, so not that big. And this Google I/O app uses coroutines, so it also uses the coroutines library, another 1.5 megabytes. Now, all of this isn't so terrible compared to the size of the entire application. That's almost negligible, but it's good to know that it's there. In addition, if you're using Android libraries, as any application, you can use the Kotlin extensions for those libraries that give those libraries more of a Kotlin feel. And these libraries are small as well. So these are just small extensions that don't take up much space. There are plenty of them though, but still small. So overall, not so bad. I'll then look at a number of typical Kotlin constructs that you might have in your own code. And I'll start with the simplest example that I could find, type aliases. And in the code of this application, I could find a type alias here that is set to be a pair of two types. And later on, elsewhere in the application, that type alias is being used as the type of a parameter of a function. Now, if you look at the compiled bytecode of this, it compiles to what you would actually expect. The type alias is gone entirely, and it only leaves the definition that was there originally. So a type alias is essentially a macro, and it doesn't have any impact on size or performance. So that was just a simple start. Let's move on to another common construct that is data classes. And the data class is a very compact way to write some code at least. And in the example for the scheduling app, I could find a room data class, and it has two properties, an ID and a name, both strings, and it has another property that is just a getter for an abbreviated name. Now, if you look at the compiled bytecode, as sort of expected, I guess, because it's documented in the Kotlin manual, you'll see that there are these two expected fields, ID and name, and to access them, there are three getters for the abbreviated name, for an ID and name themselves. And in this case, it's an immutable class, so there are no setters. In addition, there is a constructor with the two properties again. And less commonly known, perhaps, there are two methods in this case that are similar to the getters to access the fields that are there. And this is to internally in the Kotlin compiler deconstruct instances of this room class if you ever use deconstruction in your code. So that's not necessarily so, but the code is already there. And additionally, there are two copy methods that help you to create new instances of this room class. And finally, there are the promised toString, hashcode, and equals methods that have their default implementations. So this code is always generated, irrespective of whether these methods are actually used elsewhere in the application. And we'll see what optimization does to that later on. As a final example of a construct that Kotlin generates, I'll discuss briefly null checks that are in the application. So as you know, Kotlin is a type-safe language, and it's also aware of nullability of types. And that is unlike Java source code or Java bytecode. And in order to solve that or to implement that, Kotlin compiles null checks, null assertions into your code. And this is an example where the intrinsic class is called with check parameter is not null. And as an argument, it gets hard-coded the name of the property or the field that is being checked here. Now, in theory, that wouldn't be necessary if all your code were written in Kotlin, because Kotlin is aware of nullability. But conceivably, this class might be used in Java code where Java can't promise that this is not null, and then Kotlin wants to make sure, add a sort of seatbelt to ensure that these two arguments are indeed not null when the rest of the code is executed. So again, this is a little bit of overhead in terms of size, a little bit of overhead in terms of performance, because these methods are executed at runtime. So that begs the question, what happens if we start optimizing the app? And the way to go about that is the standard way in Android. We enable the minify enabled flag for debug build types, but more typically for release build types to start optimizing and obfuscating the application. Now, by default, you'll get the R8 optimizing compiler then, but at this point, you still have the option to run ProGuard also, or alternatively, by specifying either of these properties in your Gradle properties file. Of course, ProGuard is still my favorite open source project, so I've been experimenting mostly with ProGuard here. The first thing you'll run into when you run ProGuard, when you enable minification, is a lot of warnings, most typically. And that is oftentimes due to all of these small inconsistencies in the code because of minor incompatibilities in libraries or libraries that aren't present. But in this case, there is something special happening. There is a warning about some very obscure class with lots of $signs in its name that can't find a reference class that also has $signs in its name. And we had to look into what was happening here, and it turns out that the Kotlin compiler generates this reference in some metadata in the Kotlin or the compiled Kotlin class, and it refers to a class that indeed doesn't exist. I'm sure that this is a small glitch that will be solved over time, but with ProGuard, we can just work around it. We can reassure ProGuard that this is not a problem and specify the don't warn option. In this case, specifying that all classes that match this pattern can be ignored if there is some small issue like this with it. So then ProGuard takes our word for it and continues merrily processing the application. Looking at the result of that, we originally had these 16 Dex files and resulting in an APK file. And by optimizing that, it gets reduced by 73% in terms of Dex file size and 55% overall for the resulting application. So that already shows that it's very useful to process your application to optimize it. But I should note here, of course, that this improvement is not necessarily due to inefficiencies in Kotlin code that get removed. This is mostly because your application is using libraries, and it's typically just using parts of those libraries. It's not using all classes, and in the classes that it's using, it's probably not using all fields or all methods. And this is what ProGuard and R8 do. They analyze what classes the code is actually using, what fields and methods, and it removes everything that is not used. In addition, it applies optimization to the individual instructions, so it may remove unused instructions, it may propagate constants, and so on, and that may lead to further size reductions like classes, new classes that appear to be unused, but that typically is a smaller reduction in terms of size. It does improve runtime performance because any instruction that is not necessary, where a constant can be propagated and so on, that is one instruction less to execute, so to speak, and an improvement in performance. The part of Kotlin that is optimized here is not quite clear. So I'll go into a bit more detail out of curiosity to see how the Kotlin code, the Kotlin specific code, is optimized. And I'll go back to the room data class. As you remember, it had these generated methods, these getters, the component methods, the copy methods. And if you look at the resulting optimized code, indeed, as expected, or at least hoped for, the unused methods have been removed, like the component and the copy methods, they were unused. And the getter methods, they were used, but ProGuard could inline them and then remove them. And for that purpose, it also had to make the private fields public so that it could access them directly from the other classes that access these properties. That is not a problem in a final application. So in a final application, you don't care about having a clean design anymore. You want code that is as fast as possible. So that's what's happening here. Maybe interesting here to note is that the toString method, the hashcode method, equals method, they all remain in the code. In theory, you could imagine that toString is never used in your final application. But it's very hard for an optimizer to prove that that is actually the case. The room instance might be added to a list at some point, and perhaps that list is printed out at some point, and then the toString method would be used. But it's very hard to prove that in general, and typically these toString hashcode and equals methods will remain in the code. Then moving on to the null checks that we saw earlier. As you remember, the Kotlin compiler is inserting these assertions, these method invocations. And in some cases, ProGuard and R8 can remove them because they can prove that these arguments are indeed always null. or never null. But that might not always be the case, and we still want to remove those invocations. And we can do that by telling ProGuard that all of these methods don't have any side effects. They don't return a value, and if they don't have any side effects either, then their invocations can just be removed. ProGuard will take your word for it and just remove the invocations, and you'll get cleaner code. Maybe as a small tip here, you can write that in shorthand by using wildcard. You can say remove all the methods that start with check and that have any number of parameters of any type. And just verifying the result to make sure that this is actually happening. If you look at the optimized code, you'll indeed see that these invocations in the bytecode have been removed, and the only thing that is left is the actual code of the constructor here. Somewhat disappointingly to me, the overall gain of optimizing this isn't so big. So in this application, only 32 kilobytes of code was removed. So all of the invocations and eventually also the method definition in the Kotlin runtime could be removed. So that's just a tiny fraction of the overall application, but it always gives me a warm and fuzzy feeling if you can remove these invocations and at least get that little bit of performance improvement in this case. So far I've been talking about the Kotlin bytecode that is added as libraries or inserted into your application. But Kotlin also adds metadata for all of these Kotlin constructs. And I'll go into a bit of detail talking about how this is represented and how this affects your application and in what ways you should be aware of it when you process your application. So first of all, why would there be metadata? Since all of the code is already compiled to all of these utility classes and getters and setters and toString methods, and they just work. Well, there are two reasons, two typical use cases. The one is libraries, where you might be writing a library, a Kotlin library, and that Kotlin library might be used by someone else who is also developing Kotlin in Kotlin code. So even though all of the information is there needs to be some metadata that ties all of this together to properly use it in the Kotlin compiler. And the other use case is reflection in your own code. And I'll talk about some examples in later slides. Maybe I'll take a quick detour about how this is represented. This is mostly curiosity. It doesn't matter too much to your processing your own application, your own build process. But the Java class file structure and similarly the Dalvik class structure and the Dex file structure, they typically have a version of the class file. They specify the superclass and interfaces. They have lots of constants like integers, strings, method references. And then they have the fields and methods that you've defined in your source code. And finally, they have attributes. And these can be partly optional attributes, like an attribute that says whether a class is deprecated or not. And this class file format is understood by various compilers and virtual machines and so on. Now, this is a format that is specified and governed by the OpenJDK process, which is a very slow process, but it occasionally adds new elements to this class file, like perhaps new constants, new instructions, and maybe new attributes as well. Now, the Kotlin compiler is moving a lot faster than that, and they have used their own way to represent the metadata. They can't affect the main structure of the Java class file structure. They have added a metadata annotation, which is a kind of attribute. So that allows them to more freely develop extensions of the class file format that get ignored by tools that don't understand it, but that gets used by, for instance, the Kotlin compiler. Looking at the structure of this annotation, it's just a small annotation with just a couple of fields. The actual names are shorter than what I'm showing here, but this is the essential structure. There is actually the whole world behind this. It's far more complex than this simple annotation suggests. There are different types of metadata, and there is an array with strings that are actually encoded protobuffer data, and then there is an array of strings that are referenced from these protobuffer data that contain names like class names, fields names, function names, property names, and so on. So all of this is more convoluted than meets the eye, but luckily the JetBrains developers have defined or shared the Kotlin metadata library that allows you to manipulate these data and work with them as an API. And that's what we've done. So this API is still non-trivial to work with, but we wanted to look at the data that are present in these Kotlin metadata. And for that, we have created a tool that comes in two flavors. On the one hand, there is this online version of the tool where you can upload your APK file, and then you can browse through all of the classes and look at the Kotlin metadata in those classes. For instance, here I've opened the room class, and you can see the Kotlin metadata that are displayed here. In its different shape, the tool also comes as an open source project that you can download and run locally on your own computer to look at the same metadata in the same or in the console in this case. And I'll look at the data for the room class in this case, where you can see that essentially all of the structure is captured in the metadata here. You can see the different properties, you can see the functions, you can even see the equals hash code and toString method. You don't see the implementations for those. They are still in the bytecode, but the metadata essentially contain all of the structure and the names that are relevant. And that's important to note here that this tool isn't looking at the bytecode. It's purely looking at the metadata, and all of this information is in there. So this is, again, this whole world of information that is hidden behind that single annotation. In addition to the annotation that are inside the class file, there are also metadata files alongside the class files or the Dex files, and these contain similar information for the higher level functions that aren't necessarily associated with some class or another. I'll then move on to why this is important for reflection, for instance. You probably know reflection in Java. There you have a class for a name construct in its simplest form. It gets the class name, and at build time, it's not known perhaps what name is being passed in here. In that case, you need to tell ProGuard to keep the classes that are relevant in the code with their original names. Otherwise, ProGuard might rename the class, breaking the code, or it might even remove the class if it doesn't seem used, also breaking the code. So this is why you need those keep options in your configuration file. Now there is a similar concept of reflection in Kotlin, but they have extended it. You can ask for a qualified name, you can ask if a class is a data class, and so on. And this is where you need those metadata. And for that, if you start processing the code, optimizing it, obfuscating, you need to take that into account, and your obfuscator and optimizer needs to take that into account. Just like with Java, you might need to keep some classes, but in addition, in ProGuard version 7, you need to keep the Kotlin metadata, or you need to specify that ProGuard should be aware of it and keep it. Similarly, in R8, in beta right now, they have similar options to keep the relevant annotations and metadata. If we look at the resulting code after obfuscation, this is again the room class, but this time we're obfuscating this code. And as expected, the names of the fields and the names of the methods have been obfuscated to small meaningless names A, B, C, D, and so on. The toString hashcode and equals method can't be renamed because they are extending basic Java classes, Java methods. And a small nice detail here is that the default postfix suffix of this method has been preserved because that is necessary to keep the Kotlin metadata functioning properly. Then I'm looking at the null checks, and these are method invocations. They will be obfuscated normally, but you also have these field names which are actually just passed as hard-coded strings. And a nice feature of ProGuard is that it will also obfuscate those names. And I think last time I checked that R8 doesn't do that yet. And then finally, the toString method. It also contains hard-coded strings that reveal the structure of the class. And then, again, a nice detail in ProGuard is that it's able to obfuscate that as well, replacing the class and field names by obfuscated versions of them. So far, that was, again, the bytecode that I've been looking at. Now, going back to the metadata that are obfuscated. If ProGuard weren't aware of these metadata, it would just leave the annotation intact and all of the original information would still be in there. So that's something we don't really want. And with the proper setting, ProGuard does take it into account and it renames all of the properties here and the names of the functions as well. So that is working nicely. And that concludes my technical part of the presentation, but there are lots of interesting blogs online. There is an interesting blog by Jake Wharton, where he talks about shrinking an executable, so not an Android application, but a standalone executable. And his conclusion is that optimization helps a lot in reducing the size. He has an additional tip to use, perhaps if you want to really get the most out of it, to use standard classes and Java classes and methods instead of their Kotlin versions, because then you can save on having those Kotlin versions in your runtime code. Another interesting blog by Florina Muntenescu is about inlining functions. With the inline keyword in Kotlin, you can have functions inlined, which is a small saving by itself. But in addition, that can give a hint to the compiler to compile other code more efficiently. And it can save on creating utility classes and creating instances of those utility classes at runtime. And finally, there is also the blog from the R8 team where they describe how they shrink Kotlin code in bytecode, just like ProGuard does. If you want to get your hands dirty and want to do some experiments yourself, you can visit the online metadata printer that I've shown earlier at the address that you can see here. Or you can download the open source project and try it out on your own computer. If you want to delve even deeper into the Kotlin metadata, you can of course use JetBrains' Kotlin metadata library that I mentioned earlier. So that library allows you to look at purely the Kotlin metadata that are hidden inside the annotations. If you want to look at the code at a slightly higher level, you can use the ProGuard core library. So the ProGuard core library looks at the bytecode and the Kotlin metadata in combination. So it allows you to read and write the bytecode, analyze it, process it, and it's what we use as the basis for ProGuard and also for this Kotlin metadata printer. Maybe as a small note here, just to show how easy it is to use this library or how compact and concise it can be. This snippet of code visits all of the classes in the class pool that is present in a small application. And it applies a first visitor that filters the classes based on their name, in this case only looking at the room class. That one delegates to a visitor that only looks at or will visit the Kotlin metadata. That one will delegate to a visitor that visits all the functions, and that will delegate to a lambda expression that I have here that prints out the function names. So this is a very compact snippet that prints out all of the function names of the room class. It's a slightly unusual but very concise style in my opinion. So in conclusion, I've shown that the Kotlin compiler adds runtime libraries and bytecode on the code size. It adds metadata as well in classes and in separate files. And of course, that increases size, but not so bad. But it also leaks the structure of your application or your classes and the names that are present in there. So it's definitely worthwhile to apply optimization and proper name obfuscation. Now, I won't be claiming that this is protecting your application thoroughly. This is just a small part of protection. Name obfuscation is like a baby step. This is where we focus on with our commercial product DexGuard, which doesn't look just at the bytecode, but at the entire application and protecting it against reverse engineering and tampering. But that's a different story altogether. I think we'll have time for a couple of questions in a moment. After that, after this session, there is another session that you can join to talk about ProGuard and the open source project and our work on it. So you can ask questions there as well. And if you then still have questions, you can also go to our GuardSquare community website where you can visit our blogs, our forums, read interesting articles. So that's a good way to get in touch with us as well. We're happy to have launched that recently. So that concludes my part of the presentation. Now it's up to you if you have any questions. Thanks for joining and thanks for staying with me. Okay, a number of questions. What happens when I have a library with Kotlin 1.4? To be honest, I haven't tried that. If it gets that far in your application, ProGuard will optimize both of the libraries as if they were separate libraries. So that's like with any library, they will coexist alongside one another. And that is, for ProGuard, there is no special aspect to that. So the next question, are ProGuard and R8 configuration files interchangeable? Can you use them interchangeably? Yes. And I guess the only exception to that rule is the recent option that I showed. So ProGuard has added a keep Kotlin metadata option, while the beta version of R8 uses different options. But other than that, they are interchangeable. I think R8 has added some more options recently. We'll do some work on ProGuard to make sure that they remain compatible. Then the next question, how does ProGuard actually do class repackaging? ProGuard has a lot of options to repackage classes. So in some cases, you want to keep the class names, then you specify keep rules. In other cases, you want to throw all classes together in a single package and don't care about where they come from. This is the most typical use case because it's typically the most compact approach also. But there are alternative options where you can specify that you want to maintain the class hierarchy but want to have the individual package names obfuscated. So this is something that you can look at in the ProGuard documentation. So if necessary, you can maintain the class documentation, the class hierarchy, indeed. Is the two-string replacement of field names a ProGuard only feature? As far as I know, at this point, yes. I haven't seen that happen in R8. I haven't checked the very latest version, perhaps, but as far as I could see, yes. So next question. Are you expecting to update retrace to know about Kotlin stack traces? That's an interesting question. I haven't given that any thought. I'll have to discuss that with our engineering team. In some cases, it might be useful to have the synthetic methods. So it might become an option then. Thanks for that suggestion. We'll look into it. How ProGuard map already obfuscated Java class? So this is about marshalling and unmarshalling instances of classes, I imagine. If some classes have been obfuscated, then how can you unmarshal them again? That's a very tricky problem, and the general rule is there not to use reflection if possible. Otherwise, not to obfuscate the names to ensure that they are maximally backward compatible and forward compatible. And if that's not possible, you can try applying the mapping file to subsequent versions of your application, so they remain compatible. But there are some tricky issues there as the application may evolve and it may be impossible to maintain such an obfuscation mapping. Okay, next question. Problems when libraries use coroutines. I'm not aware of those problems myself, but I suggest that you report them either on GitHub or on our DexGuard community platform, and then we'll look into it. Testing obfuscated code. Yeah, so that can be a challenge if your tests rely on internal APIs of your application. So if your tests only use external APIs, then that's not a problem because those external APIs will be maintained, like activity names perhaps, or other entry points of your application. If you start accessing private classes or fields or methods, then that becomes trickier, and there are two ways there. Either you can try to obfuscate your code and your tests simultaneously so that they remain consistent, or you can try to apply your mapping file when you then post-process your tests. But this is trickier because ProGuard may have optimized a lot, for instance, inlining methods, so the method is gone entirely, or merging classes, things like that, that complicates life a lot. So I admit that this is a difficult problem. Some incompatibilities between ProGuard and R8 dealing with wildcards, that could be. In my opinion, then that's something for the R8 team to look at, because the ProGuard configuration has been around for a long time and has been backward compatible for a very long time. Okay, so that's all for now. As I said earlier, you're welcome to join us in the session after this session, where we can talk more about ProGuard and maybe experience or problems or questions that you might have. Thank you all.